name's Elizabeth Webel, and I'm a junior in high school.
And I'm Alex, a sophomore in high school and the main narrator for this video. So without any introduction, let's get to the video. This experiment illustrates the two main concepts that provide lift for any flying machine: airplane, helicopter, tilt rotor, etc. First is Bernoulli's principle, discovered by the Swiss mathematician and physicist Daniel Bernoulli. Bernoulli was born at the beginning of the 1700s to a renowned family of mathematicians. His father, Johann Bernoulli, taught Daniel much of what he knew about mathematics. He later went on to earn his MD and write a prominent book on differential equations, and most notably for this experiment, the physics of fluids. It was Bernoulli who established the pivotal relationship between pressure, density, and velocity in fluid flow and development of the famous Bernoulli principle, which states that increasing the velocity of a fluid will simultaneously decrease its pressure. With the equation that corresponds with this principle, one can calculate the amount of lift force a wing or airfoil will provide if they know the dynamic pressure of the airflow around the aircraft, which is shown by the airspeed indicator in an aircraft. The second important concept necessary to provide lift is Newton's famous third law of motion, which states that for every force there is an equal or opposite reaction. Sir Isaac Newton, an English physician and mathematician, was born in 1642 and is one of the most influential and distinguished scientific thinkers in history. From his work in the science of light to the three laws of motion to his discovery of infinitesimals in calculus, Newton made possibility the most consequential effect on modern science ever. And one of the many applications of his findings is in aviation, in which his third law of motion helps explain the force of lift. I pointed the compressor nozzle straight up and set the screwdriver at a 45-degree angle about 2 to 4 inches above the nozzle. It took a couple of tries to get it to levitate, but after a couple takes, I finally got it to stay suspended in the air. One very important note is that the curvature of the screwdriver is smooth, compared to this one, which is indented. As you can see, it didn't stay suspended as the airflow was interrupted by the dents. The reason the smooth screwdriver stayed suspended is that the air coming from the compressor made its way around the screwdriver smoothly. As it went around the backside of the screwdriver, it formed an air gap where the air wasn't moving as fast as the compressed air, causing a low pressure zone. That low pressure zone is what held the screwdriver in midair, sucking it up. The reason that the indented screwdriver didn't stay in midair was the airflow was interrupted by the dents, causing the screwdriver to fall to the ground.
As Alexander demonstrated with the air compressor and screwdrivers, lift occurs as a result of both Bernoulli's principle and Newton's third law. While curvature is not required in order to utilize these concepts, it greatly improves the efficiency of a wing to have a curved leading edge ending in a tapered trailing edge. This is where the concept of an airfoil comes from, which you can see in the image shown. Most airplanes use the teardrop design of an airfoil in order to produce more lift, and while shapes may vary, they tend to generally look like this. There is a common misconception concerning cause of lift, that being that either Newton or Bernoulli are the sole explanation for it, and that the two are mutually exclusive, the effects of one rendering the other an inferior explanation. This is incorrect. As I'll show you, mathematically the two are the same, and conceptually both are necessary to describe the force of lift. Bernoulli's equation basically describes conservation of energy for fluids, stating that pressure, in this case also potential energy, plus kinetic energy plus gravitational potential energy equals a constant. In order to apply Bernoulli's equation, you have to account for the different assumptions that it makes, the first of which is that the total energy will be constant. This means that there cannot be any added or subtracted kinetic or potential energy. The two can switch back and forth, but more energy cannot be added or removed. Thus, the viscosity of the fluid, basically how thick or thin it is, must be equal or close to zero. Thankfully for aerodynamic applications, air has a very low viscosity, so it is negligible for the most part. And elevation changes in airflow are fairly insignificant in this case as well. So the equation can be further simplified by removing the part on gravitational potential energy. Finally, there's the assumption concerning density, shown by the Greek letter rho in the equation. Density needs to be constant, meaning the fluid in question must be incompressible. For this to be possible, the velocity of the flow needs to be below the speed of sound. So while this assumption would apply to a commercial aircraft or helicopter, any aircraft traveling at or above the speed of sound will require a slightly more complicated version of the equation to account for the compressibility of air and inconstant density. From here, the equation we are left with basically states that in order to maintain a constant, as velocity increases, pressure or potential energy will need to decrease, and this is where Bernoulli's principle is applied to aerodynamics. Often this principle is misapplied with the theory of equal transit time, which proposes that airfoils are designed with a curve so that the upper surface of the wing is longer in order to generate a higher velocity of airflow on the top of the wing. This is so that the airflow above and below the wing will meet at the same time at the end of the wing. Then Bernoulli's principle is brought in to explain how, due to this higher velocity above the wing, the pressure is consequently lower and therefore produces lift.
False.
In reality, the airflow above and below the wing do not meet at the same time at the end of the wing. The air on the top surface does indeed have faster velocity, but it is actually so much faster that it travels the longer distance and reaches the end of the wing a fair bit sooner than the airflow below the wing. Therefore, the two main errors of this theory is that it often is the only explanation given to describe lift, and that it assumes the time for the airflow on the top of the wing to reach the trailing edge is equal to the time it takes for the airflow below the wing. As a result, trying to calculate velocity with the equal transit theory will give an incorrect answer. The second important concept required to describe the force of lift is Newton's third law of motion, which says that for every force there will be an equal and opposite reaction. This is how rockets work. A major force is applied towards the direction of the ground, and an equal and opposite force responds, pushing the rocket into the air. When you jump, you apply a certain amount of force on the ground as you push off, and the ground responds with an equal and opposite force that lets you get off the ground at all. This is often mathematically represented by F subscript A is equal to negative F subscript B. To calculate F, which stands for force, Newton's second law of motion must be brought in. Force equals mass times acceleration. For the purpose of aerodynamics, we can replace force and mass for the fluid equivalence. Pressure 1 times area minus pressure 2 times area for force, and for mass, density times volume. To prove that these two concepts are both important to the explanation of lift, we'll show the basic derivation of Bernoulli's equation from Newton's second law of motion. Here I've drawn a box representing a particle of air moving along a streamline. There's pressure being exerted on the surfaces of the box, represented by P1 and P2. We assume these are not equal. The capital A represents the area of the ends of the box, and the X represents the length of that box. First, we'll take Newton's second law of motion, which is F equals ma, force equals mass times acceleration, and as I previously explained, replace force and mass for the fluid equivalence, as well as get an equation for the acceleration that relates to velocity. This brings us back to the P1 and P2 variables. The reason we can assume they are not equal is because according to Newton's second law, there must be some sort of acceleration for there to be a net force not equal to 0. Thus, the equivalent for force here is pressure times area minus pressure 2 times area, which can simplify to area times pressure times pressure 1 minus pressure 2. So we would have our force here would be equal to area times pressure 1 minus pressure 2. And then the mass equivalent for a fluid would be density times volume, represented here by rho times lowercase v. So our mass is rho times v, and then our volume, which is what that v is, would be area times the distance or the length here. Now, if we imagine the box moves along the streamline with a distance about its own length, and starts with velocity 1 and ends with velocity 2, we can use the basic formula for acceleration. So, which in our case would be A equals V2 minus V1 divided by the time that it takes to travel the distance x. If we're working with a small distance and assume that our acceleration is constant, and we can assume that we are and that it is, then a good general equation for our average velocity would be, so our average velocity equation, VAG, would be velocity 1 plus velocity 2 divided by 2. To find the distance that the box traveled, we first rearrange the velocity equation of distance divided by time to get distance x equals velocity v times time. So v equals distance divided by time. We can rearrange that to get x distance equals velocity times time. So basically that. We substitute in our other equation for velocity to get this, where we will go, so we'll substitute it in to get this. X equals v1 plus v2 over 2 times t, and then we can rearrange that further to end up with t equals 2x over v1 plus v2. Now we plug in this equation for time into our original equation for acceleration. To simplify it, we'll take the main numerator and denominator and multiply each by v1 plus v2. These will cancel out, and then we'll end up, and it will look like this. So we'll plug in our numbers to the original equation, and we'll have v2 minus v1 over 2x over v1 plus v2. And then, as I say, we'll multiply both by v1 plus v2, so v1 plus v2, v1 plus v2, and these will cancel each other out, and we'll be left with acceleration equals v2 minus v1 times v1 plus v2 over 2x. Now that we have all the variables we need, we can plug them into Newton's second equation, because we now have a equation for acceleration that relates to velocity, which, by the way, we can further simplify this even more. We would get v2 v1 plus v2 squared minus v1 squared minus v1 v2 over 2x. These two cross out, and we're left with a final equation for acceleration of v2 squared minus v1 squared over 2x. Now that we have all these equations and variables that we need, we can plug them into Newton's second law. So we'll have area P1 minus P2 equal to rho times density times V2 squared minus V1 squared over 2x. Sounds very complicated, but we'll just, but as you'll see when we plug them in, it makes more sense. So P1 minus P2 equals rho times volume, and then our equation up here, v2 squared minus v1 squared over 2 of x, and then we will bring that over here. We can substitute in the equation for volume here so that we can start canceling out different variables. So we would have a P1 minus P2 equals rho times a times x for distance, and then v2 squared minus v1 squared over 2 of x. Our x's cancel out, and then if we divide both sides by a here, so divide both sides by a, we can cancel out the area here. And then we'll be left with P1 minus P2 equals rho times V2 squared minus V1 squared over 2. And this is starting to look awfully like our Bernoulli equation up here. If we start to simplify this by moving over all of the velocity, or V1 bits of the equation over to this side, to the left, and then moving all of the pressure to the P2 variable to the right, we would end up with P1 plus rho times V1 squared over 2 equals P2 plus rho times V2 squared over 2. Now, no matter how many times the box moves a distance of x, this equation will always simplify out into an equality, meaning that it is a constant. So we can rewrite this into its final answer as pressure P plus density rho times velocity squared over 2 equals a constant. And we're right back to Bernoulli's equation.
So in summary, there are 3 points to remember. 1. Newton and Bernoulli's concepts are both necessary to describe the force of lift. 2. Bernoulli's principle describes how the increased velocity of the airflow on top of the airfoil decreases the pressure above the wing, creating a downwash. Due to Newton's third law, the air below responds to this downwash with an upwash, pushing against the bottom of the wing. All this works together to create lift. And finally, an airfoil requires a smooth surface in order to produce lift. And with that said, that wraps up our explanation of how lift is generated. Thanks for watching.